Okay, so last time we've talked about triangular element. This time we'll go to 2D rectangular. But we will 2D rectangular, but we will use the isoparametric element. Okay. Now, for the isoparametric element, so ito yung parang ano niya, no? Magandang illustration for that. So for example, meron tayong rectangular element like this here. And ito yung in real world, say ito yung element natin. Hindi siya regular rectangle. We will transform this element into a say a regular rectangle here. So ganun yung idea ng isoparametric element. Kumbaga, yung shape function natin, as we've been using doon pa lang sa axial, sa beam, sa triangular element. According sa concept ng isoparametric, yun din yung gagamitin natin shape function to transform this real world shape na irregular pero four corners into a isoparametric element na ganito yung itsura. Take note, yung itsura niya is bounded lang siya from negative to 1. For example, dito 1, 1, dito negative 1, 1, dito naman negative 1, negative 1, and then 1, negative 1. Parang you can look at this as a simple Cartesian coordinate system, no? Na ito yung coordinates niya, no? So from a real world na iba-iba yung coordinates, we will transform that into this na ang coordinates is all 1, na iba-iba yung sign. Okay? Okay. And then, so for the coordinate transformation, dahil nga magta-transform tayo, so ito nga yung sinasabi ko na the geometry of an element may be expressed in terms of an interpolation function. Ayan. Okay. Then ito naman yung coordinates of nodal points of the elements. Okay. Now, since itong Cartesian natin, for example, is in terms of x and y, pagdating dito sa ating element here on the left, hindi na siya function ng x and y. It's now a function of theta and okay. Okay, so from this xy Cartesian coordinate, it will now be in a theta and eta coordinate system. Kaya nga, ito yung tinatawag nating natural coordinate system. Okay. So, next is, okay. So, when you transform that, so, okay, we need to transform that using the chain rule, no? Okay. Nandito tayo sa ating, okay, we will transform that, plate bending pala to. Where is our lecture here? Rectangular, yeah, okay. So, according sa ating chain rule, which is isoparametric, yan, isoparametric here, yan, okay. According sa ating chain rule, okay, of partial differentiation, no? So, to get the partial derivatives of a function in terms of, say, the theta, no? Pansinin nyo, no? d dx and then dx d theta plus d dy dy d theta. Okay. Okay, pansinin nyo, no? d d zeta equals d dx dx plus d dy dy d zeta. Okay, pansinin nyo. Ano napansin nyo? May pwede tayong i-cancel dyan. What's that? So, pwede natin ito i-cancel. That's why chain rule applies. Right? Cancel ko to. Cancel, cancel, cancel. So in short, saan yung pen ko? Here's my pen. Yan. No? Therefore, equal sila. For this chain rule. So, we will do that. Okay, when you do that, ito ang mangyayari. So, in matrix form, get the matrix form of this. Okay. So, get the matrix form of this, you will come up with this. Okay. So, ddc over dd eta is equal to, yan, yung matrix na yan. Ito. This one. Multiplied by a column matrix ddx over ddy. Now, i-extract natin to. Okay. So, yun nga, no? So, i-extract, i-state tong ddx and ddy. Then, we will call this matrix na to, yung nauna sa kanya, as our Jacobian. Jacobian matrix. Yan. Okay? In fact, even if you study numerical, no, methods, anything na, lalo na sa partial differential equation, no, laging may Jacobian yan eh. No, because parang yung Jacobian matrix kasi, parang yan yung scaling factor. No? Kasi from a real world geometry to an element na bounded lang ng -1 to 1, kailangan mo ng transformation. No? You are transforming, di ba? A real world geometry coordinates to an element, a natural coordinate system. Okay? And that's why you need the Jacobian matrix. And by the way, bakit natin tinatransform into a natural coordinate system? To be able to use the Gaussian quadrature numerical integration. Sa numerical integration using Gaussian quadrature, or Gauss quadrature, yan, numerical integration, ang boundary natin, ang limits natin will be from -1 to 1. Tapos, this is your function. dx. Diba? Remember, our KK, or the stiffness matrix, it's a volume integral, diba? As we've been solving, no? K typically is B transpose dB, no? As we've been talking about, no? Ayan, no? So it's an integration. So it's an integration, volume integral. And we are using Gauss quadrature. Okay. Now, so that's your Jacobian matrix, which comprises of dx dc, dy dc, dx d eta, dy d eta. Okay. And I want you to concentrate pa ulit kasi lagi nyo nga itong gagamitin. We are, in effect, parang kinukuha natin yung partial derivatives ng function with respect to the dc and d eta. No? And since two-dimensional, which is a function of x and y, kailangan mo rin ng two-dimensional na natural coordinate systems, which is c and eta. Okay. So x equals summation of nixi. Okay. 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 So what is dx/dc? Since we know here that x is summation of n matrix or shape function xi, therefore, since kinukuha natin yung partial derivatives ng x with respect to c, so ipa-partial derivatives mo din yung right side equation na ito, no? Okay? That's why ito is here. So all the Jacobian matrix here will be now this. Okay? Kasi it's a partial derivatives. Get the partial derivatives of this. Ito na siya. Okay? Next. Now, in real world, what we wanted is the partial derivatives in terms of x and y. Kasi nga, it's a function of x and y. And since we transform that into a natural coordinate system in terms of c and eta, therefore, your Jacobian matrix will need to be inverted. Okay. Which is J inverse. Okay. Okay. Again, if you look back if you recall sa triangular plates natin, or rather triangular element, yan, if you recall sa ating triangular element, okay, we also, well, to be consistent with elasticity, we need strain, no? For two-dimensional plane stress formulation, yung strain vector natin is ito, no? Strain x, strain y, saka yung shearing strain na xy. And we know that from the plane elasticity, or rather from elasticity, that strain x is du dx, strain y is dv dy, and shearing strain xy is dv dx plus du dy. Okay. Now, remember this, okay? ddx, ddy, and look yung analogy ng dalawa, okay? So that means any function partial derivatives with x, parang ito, du dx, okay? And then we have ddc and dd eta, ddc, dd eta, okay? Therefore, yung J inverse natin is actually a composition of J11, J12, J21, J22. Yan, yung mga yan. Yan yung J inverse natin. Okay. And then this, oops, nawala. Okay. So, in expanded form nito, ito siya. Okay. Okay. From the partial differential partial derivatives from real world coordinates, ito yung itsura niya. This is the partial derivatives to a natural coordinate system. Okay, so we further we will further extract yung Jacobian nito inverse. So ito na siya. Okay, so naging du dc, du d eta, dv dc, dv d eta. Okay, and then the inverse Jacobian is ito na siya, J11, J12, J21, J22. Okay. Okay. Now take note, this is two-dimensional, no? So, pag 3-dimensional, so, I mean, 2 degrees to displacement per node na rectangular, right? So, kung 3 displacement yan, what do you think? Ang size. So, hindi ko ma-zoom in no? Okay. Yan, no? Okay, so therefore, magiging tatlo to. Tapos another 3, that means 6. 6 element lahat to kung gano'n. No? If we're talking about 3 degrees of freedom per node. On the case of plane stress, plane strain kasi na 2-dimensional, we're only dealing with 2 degrees of freedom. Okay? Kaya naging 4 to. To be consistent with our matrix here, this becomes 3 by 4. Okay? Recall natin, no? So this is 3 by 4. 3 by 4, while this one is 4 by 1. So tama naman, no? Same size sila, therefore this becomes 3 by 1, which is this. No? This is 3 by 1. The strain vector. Okay? Next is here. Remember, in triangular, what did we discuss? Strain is actually BD. Yeah, no? Strain is BD. Okay? The B matrix. Okay, but before that, alam na natin to, strain is, but what is du dc, du d eta, dv dc, dv d eta? Where is that? Here. Okay. Okay. Now, du dc, okay, will now be this. No? So, right? Because u, as we know, is, tuloy, lagay ko dito, u is equal to n ui, di ba? NIUI, no? So, kung kinuha natin yung partial derivatives ito, kukunin din natin yung partial derivatives ito, no? Kunin mo din yung partial derivatives niyan. So, ito siya. Okay. Yan. Okay. Get the partial derivatives here. Ito yung partial derivatives. See? Okay. So, further. Okay. Okay. So, strain is BD. That means B is actually this. That is our B. And this is D. Displacements. The displacements. Which is what we need sa, sa ating theory. So, finite element. We get the displacement first. Okay, so therefore the B matrix is this and this. Okay. Okay, so balikan natin, no? So from here, strain is this na nanggaling dito, Okay. Okay. But this one, du dc, yung mga yan, is this. Okay. So, i-plug in natin daw ito sa strain na ito. Okay, yan. Pag plug in mo yan dyan, ito na siya. Okay. So, ito na siya. This is the B. Okay, so pansinin nyo din, no? Even the area, no? In real world, dA is dx dy, no? In a natural coordinate system, this now becomes j dc d eta. Okay? Kaya nga even the area, pag transform mo into natural coordinate system, the dA becomes j dc d eta. Okay? Now, ito yung sinasabi natin kanina, no? Stiffness is B transpose dB, volume integral. Okay. Since T, let's assume T should be constant. We can now extract this. The differential volume becomes now T times dA, right? Kasi constant to, in-extract siya dito. But since dA is this, this now becomes, hindi ko pala na-capture. Yan, ito pala yun, no? Sa baba. Okay? This one becomes this. Okay, yan, okay? And ito yung in-extract natin na T. And then, still, nandun pa rin yung B transpose dB. No? As consistent with our concept, since axial, since beam, since triangular element. Okay, and again, dahil Gauss quadrature ang gagamitin natin, our boundary is from -1 to 1. Okay. What else? So that's it. No? So let's try to solve a problem. Okay. Okay, so here's an example of a plane stress problem. So dito lang, kinukuha lang naman dito yung stiffness matrix. Because remember, pag nakuha mo na kasi yung stiffness matrix, invert mo lang yon, multiply with the force vector, makukuha mo na yung displacement. So focus lang tayo sa stiffness matrix muna. Okay, so medyo ano ko yung window para makita natin yung mga ginamit nating formula dito. Okay, so calculate daw the stiffness matrix of a given 4-node rectangular element by the Gauss quadrature integration rule using 1-point and 2-point formula. So ang gagawin natin is 2-point Gauss quadrature na. Consider the thickness of element 20 cm. That's why meron ako ditong variable na thick or THK is equal to 20 and E is 2 times 10 raised to 3. Basically, for sure, this is 200 gigapascal. No? Okay. Then mu equals 0. Okay. Okay. That's it. And now, actually, andito siya. Kinuha ko lang naman yung problem dito. So, lecture notes natin from NPTEL. Where is that? 2-point. Yan, ito siya. No? So, the first step is for a 2x2 Gauss quadrature kasi, no? Okay, ito yung mga, here are the sampling points natin. So, 1, 2, 3, 4. 2x2. No? Okay, remember, yung natural coordinates natin, 1, 1, -1, 1, -1, -1, 1, -1. Therefore, kailangan mo rin ng 4 na points. And yung points na yun are this. Okay, for a 2-point Gauss quadrature, this is constant, no? Hindi, ano to, no? Given siya, okay? So, every time you use Gauss quadrature, no? Constant yan, no? Okay, then, first step, what are the shape function of a 4-node quadrilateral? Ito siya. Okay, so on a separate video, diniscuss ko to. Okay, 1 minus C, 1 minus eta. Tignan nyo. Papasin nyo, pare-parehas lang. Nagbabago lang ng sign. Okay? 1 plus C, 1 minus eta. Okay. So, ito yung shape function in a natural coordinate system. Okay? And then, you notice, sa lecture din dito, kailangan natin makuha yung partial derivatives, diba? dn dc. Yan, dn d eta. So, we need to get the partial derivatives of that. Okay. Okay, so from that problem, okay, so you get the n matrix or the shape function, which is this, no? And then get the partial derivative of those. Halimbawa, itong 1 minus c, 1 minus eta over 4. Since we are getting dn over dc, so constant itong constant itong eta. Okay? So parang ito yung x natin. So 'di ba, ang natitira is the constant. Yan, no? That's why negative 1 minus eta all over 4. Okay? dn 2 over dc. So therefore constant ulit ito. So as is to 1 minus eta over 4. dn 3 over dc. Constant ulit to. 1 plus constant coefficient, 1 plus eta over 4. Okay, so on and so forth. So ganoon din dito. So once you have this, yung mga yan, the Jacobian matrix will be this. Okay, ito. Okay, as what we discussed earlier. So plug in lang natin, no? Tn1, plug in natin itong mga to, yung mga nakuha natin yan dito as our Jacobian matrix. Okay? So mapapansin nyo yung ating real world coordinates, yung mga yan. x1, y1, x2, y2, x3, y3, x4, y4. Okay? So you need the Jacobian to transform this real world coordinate Cartesian coordinates. Okay? So next is, ito na. So when you plug in those values, remember yung theta and yung c and eta natin, may values na yun, no? Earlier. Which is, where's that? Ito. Okay, yan, no? Pala na. Okay. So, yan yung values natin dito. Okay, yan. Yan, okay. Because what I will show you is yung sampling point using yan, no? 0.57735 and 0.57735. Kumbaga ito yung ano natin, C, and then ito yung eta, no? Mali pa, parang hindi eta. Yan, okay? So when you plug in dyan, yung mga itong dalawa, you will come up with 35,0,025. Nakita ko simultaneously with the SMATH, which is this. Right? Ginawa ko lang siyang S matrix. So ito yung coordinates. So node 1, 0, 0. Node 2, 70, 0. 70, 0. Node 3, 70, 50. And then node 4, 0, 50. Okay? Then ito yung gagamitin nating sampling points. Okay? Then the N matrix is here. This one is actually this one. Yan, no? 1 minus c, 1 minus eta over 4, 1 plus c, 1 minus eta over 4, 1 plus c, 1 plus eta over 4, and then 1 minus c, 1 plus eta over 4. Okay. Next is, so dndc, yung value nito is simply this one. Okay. Pinangalanan ko lang siyang variable na dn1. No? Pero yan yung actually yung dndc. Okay. Yun. This one yun. No? Okay. Then, I was able now to get my Jacobian. Jacobian is dndc times the matrix of the coordinates, which I named as dim. So, multiply mo yung dalawa, kagaya dito, and that's your Jacobian, 35 and 25. So, the same with our lecture here, notes here. And then, you may now get the inverse of that. Kasi ano naman yan, no? Numbers naman yan, no? Real numbers naman yan. Okay? Therefore, your Jacobian is 875. Okay, parang yun yung scaling factor natin. From the real world coordinates to the natural coordinate system is 875. Okay, okay na tayo. Nakuha na natin yung Jacobian. Then, let's now find, supposedly, we need to find now the strain matrix, strain vector. Okay, ito yung formula natin earlier. We've been discussing. But strain is BD, di ba? Strain is BD. Strain is BD. Ito yung kailangan talaga natin, yung displacement. But kailangan natin makuha si B, which is this one. This is our B. D and DC, alam na natin yung mga yan, no? From here, okay? But what is our J11, J12? We should know this kasi nakuha na natin yung ating inverse of Jacobian. So, ito siya. Oops, yan. Mapapaito. Yan, okay? So, the B is, ito yung J11 natin is, yan, J22, ito. Okay. So, walang value, 0 ang J12, according here, no? So, J11, ito, J22, okay? J21 is 0, J22 is this, J11 is this, J12 is 0. Then, multiply that with this matrix. Ito yon. So, nasan yung SMATH implementation niya? Ito. Yan, okay? So, ginawa ko lang siyang ano. Ito yung SMATH implementation niya. Of this. Yan, okay? Parang, ito yung gene matrix, no? Okay? Then, pinangalanan ko itong JB muna. Itong B. Okay? Jacobian inverse. Okay? Then, ito naman yung DN matrix or DNDC, DND eta. Okay? Which is ito. Okay? So, therefore, this is the B matrix. B is equal to JB, B matrix. That's it. No? Next is, now know that, okay, alam na natin yung B. Okay, malapit na tayo, no? Remember, K is integral of B transpose BB. So, alam na natin yung B, no? D is actually, this is constant, no? From the plane stress condition, ito yung formula ng ano, D or C. In our case, for plane stress, pinangalanan lang natin siyang C. Okay? Okay? From plane elasticity, na-derive to, no? From elasticity theory, no? Na-derive yan, no? So, plug in mo lang yan, no? E is given, mu is 0. Okay? As given sa problem. Okay, that's it. Okay na tayo, no? That's our K. Okay? So, this is the C. And then K, since we are using Gauss quadrature, ito yung formula natin. Okay? Thickness, Wi and Wj is both 1. Okay? For our first sampling point. Okay? J is, we know this already. So, operate mo lang yan sa SMATH. we get this. K1 pa lang yan. Because, yan pa lang yung, ang ginamit pa lang natin dyan, yung una nating sampling point. Now, you will repeat the same process 4 times. 4 times, yeah. And then, yan yun. May K2 ako, may K3, may K4, and then add them all up. And that is your final K. Okay, kaya medyo mahaba itong code na to. Okay. And what do we got from our problem? Your K should be, where's that? K is, in our lecture, should be this. Okay, that is your final K. Okay. Take note, ang babaguhin mo lang naman sa ating methods for K4 yan. Yung value ng C and eta. Okay. Okay, that's it. Yun lang. Then I paste it here. Okay. Oops. So, maximize natin. Eksakto ba? Oops. Hindi ko siya mapalaki. Anyway, maximize. That's it. So, mukhang, ano naman. Sakto naman, no? Naka 10 raised to 4. Naka-multiply pa siya sa 10 raised to 4. So, definitely, parehas sila ng value. Ito, kailangan mo pang expand. Yan. Expand. Okay? So, that's it. That is a SMATH implementation ng plane stress using rectangular isoparametric element. Okay.